Okay, in this video, we're going to look at, first of all, electric motors, because we can bring in some of the stuff we've learned on Faraday and Lenz's law to better explain motors. And then we're going to look at generators, that are a way of producing electricity that we use in the national grid today. So starting off with motors. If we look at our diagram over here on the left-hand side, we can see we've got field lines going across from north to south. So our first finger is going to point across that way. On the left-hand side, we've got current coming out of the page. So that's our middle finger goes that way. So on this side, we experience a force in this direction. On the other side, the current is going in the opposite direction. So we produce a force in the opposite direction. So why do we get a force? Well, we've got a current traveling perpendicular to the magnetic field. So that's why we've got a force. And on opposite sides, the current is in opposite directions, so we produce forces in opposite directions, and that's what we can see here. So the turning effect, or the moment of these forces, acts to cause the motor's rotation to accelerate. So if it's stationary to start with, it's going to rotate faster and faster until it reaches a terminal rotation speed, if you like. So that's what's going on with our motor as a general idea. It's essentially a moments type problem. Okay, so how can we update that now? Well, what does Lenz's law tell us about the motor when it starts to spin? Well, so once the motor starts spinning, there is now a conductor, because remember, a motor is wrapped in coils of wire. So we now got a conductor cutting through a magnetic field, which we've seen in previous videos will induce an EMF. And because it's in a complete circuit, that EMF is going to cause a current. So that's what Lenz's law tells us, or that's what Faraday's law tells us, sorry. Lenz's law tells us the current will oppose the motion of the motor. And so it will be in the opposite direction to the current already in the motor. So remember, to get the motor to spin, we had to put a current through the coil in the motor. So that's what we're talking about. When we talk about the current already in the coil, we're talking about that one. Lenz's law tells us we're going to induce another current, but in the opposite direction. So the effect of it is to reduce the current inside the coil, and that reduces the turning effect. So that reduces your maximum spinning speed as well. So that's what Lenz's law tells us about the motor. So just a quick reminder, because we're going to have a similar type device for a generator. What was the purpose of the commutator? Well, it was there to reverse the motor current direction every 180 degrees in order to keep the motor rotating in the same direction. So that was the purpose of the commutator. So let's now look at a generator, and we'll see how it's different. So a generator has these devices at the bottom called slip rings. So you can see it's these cylindrical type things at the bottom. So they have a different function to the commutator, even they look like they're quite similar. So slip rings are a complete ring. There's no gap in the ring. So slip rings allow you to connect the generator to a circuit without the wires becoming tangled. So what you have is this wire will just follow this cylinder around and maintain a connection. This one will just follow the cylinder around and it will maintain a connection. So it's a way of having a stationary circuit connected to a moving device. But here's the key difference: they do not reverse the current direction. They're just there to give you a better connection to the circuit. That's all we use slip rings for. Okay, so we're going to talk now about how generators work, and why they produce this AC, or alternating EMF. And we're going to be talking about these sides, which are the AB side, this one here, and the CD side. These are the key ones in terms of what's going on with a generator. What we've done is we've now got a side-on view. So AB and CD are now into the plane of the page. And these arrows indicate the direction that AB and CD are traveling. Okay, so in this first diagram, the A, B, and CD, or the wires going into the plane of the page, are moving perpendicular to the magnetic field. And that means you're going to be cutting the maximum number of flux lines per second, inducing a maximum EMF. Okay, so in this position, you're going to get a really big EMF produced. In this second one, the wires going into the plane of the page are moving parallel to the field lines. So you'll notice this velocity arrow and the field lines are in the same direction. So no magnetic field lines are being cut, and so no current or EMF is induced in this position. So we've gone from here, producing maximum EMF, it rotates 90 degrees and it produces no EMF. So we're starting to see how we produce the alternating pattern. Look at what the whole thing looks like. So if we have a motor do a complete rotation, this is the waveform that we produce. So this first one here, these points are moving, so this one corresponds with this point over here. So A and B, remember, are moving parallel to the field, and therefore no flux lines are cut, so we get no EMF. A and B are now moving perpendicular, so we've got this position, maximum EMF. This one is essentially the same as the first one, but the other way up. So in this one, you'll notice that B is now going upwards, whereas A is going downwards. So we can see that B cuts through the field in the opposite direction, which is why we produce an EMF in the opposite direction. And then finally, we're back to this position again, and we're not inducing an EMF at all. So the key thing is whether the side that is into the plane of the page is moving perpendicular or parallel to the field lines. That tells us what the EMF going to be induced is doing. And the reason the EMF decreases is the number of flux lines per second that are cut decreases as the angle between the velocity and the field lines increases. We cut through fewer field lines per second until we get to 0 when it's parallel.